Hello there, Mr. Sutton here, bringing you the Algebra 2 4-5 lesson on solving polynomial equations. So this is going to be either a 3 or a 2-parter, depending on which version of the course you're taking. Either way, through this one we will be solving polynomial equations by factoring, and we're going to be graphing polynomials in standard form. The factoring is going to help us with that. And then we'll go back to do some more solving polynomials, but this time we're going to be using the rational roots theorem instead of traditional factoring. So we are going to dive right in with an equation here. 8x cubed equals 72x. We're trying to solve this thing. So just as a little bit of a hint before you dive into this one, I would say when in doubt, zero it out. Most of our techniques involve having 0 on one side of the equation, so that's probably a good way to start this one. Pause the video though and do it however you see fit, and let's see what you get. Alright, so I'm going to take my own advice and move this 72x over to the left side to get 0 on the other side. Now another thing that might be tempting in this situation is some people might want to divide by x. And we have seen in the past that dividing by x is bad news. We don't divide by variables, specifically because you might be dividing by 0, which is always a bad idea. So instead of dividing by a variable, it is better to take out a GCF. We should always try to take out the GCF in the beginning. And there's a few more things other than x that we can take out of this one. 8 and 72, both divisible by 8. So we can take an 8x out of this whole expression, and that leaves us with x squared minus 9. Now once you've got down to a quadratic factor, quadratic factors like this x squared minus 9, remember we have a lot of ways of dealing with that. You could factor it a little bit further. That certainly is something you could do in this specific case, but that won't always be an option. So if factoring is not going to work, you can also square root. You can also use the quadratic formula, or if you like, completing the square. Either way, so lots of techniques to use. In this case, I think factoring will be, it's not necessarily the fastest, but I'm showing this thing completely by factoring, so I'll show you this approach. So we have the 8x we took out initially. This is a difference of squares, so I can use the a plus b, a minus b shortcut and break this up into x plus 3 and x minus 3. And then setting each of these factors equal to 0, just like we did when we were solving quadratics by factoring. If 8x equals 0, then x equals 0. We got negative 3 for this second parentheses to zero that out, and 3 for the last one. Now if you'd wanted to, you could have set x squared minus 9 equal to 0, added the 9 and square rooted both sides to get you this plus or minus 3 as well. So lots of ways to do this one. For this next problem, we're going to throw a little real life situation in here. So let's say that in a time of economic turmoil, a country's rate of inflation can be modeled by this polynomial function below, where x is the number of months since the start of the new year. Now you might be wondering, well, where is this formula even coming from? And we talked about this before, but polynomials are kind of chameleon-like in how they can be shaped. So you can really get a polynomial to model pretty much anything you want within a certain limited amount of time. Eventually they veer off into infinity, but between then you can make it look like a lot of different things. So we want to know for this problem at what times are prices neither increasing nor decreasing. Inflation equals exactly 0. So this is a case of needing to find the zeros of a function, which basically just means we are setting our function equal to 0 and solving. So pause the video and using the factoring techniques you have at your disposal, see where you can get with this one. Now since I have 4 terms in this one, I'm going to try the technique of grouping. I first looked to see if there's any GCFs I can take out of all 4 of these terms, and there are not. So let me try grouping instead. For the first 2 terms, I can take an x squared out of those. That leaves me with x minus 5. And for the next 2, I think I can take a 32 out of those, a negative 32. That'll leave me with an x, and 160 divided by negative 32 is negative 5. Excellent. So I have a common factor of x minus 5 that I can pull out of everything, and then this x squared minus 32 is my leftovers for the other parentheses. So let me set each of these parentheses equal to 0 and solve it now. 5 minus 5 is 0, so that's going to be one x value. And for this other one, If I add the 32 over to the other side, I can use x squared equals 32, and then I can square root both sides. 32 is not a perfect square, but it does have perfect square factors, so I'm going to be able to break this up a little bit more. Specifically, if I split 32 up into 16 and 2, that'll help me out. So I'm going to have plus or minus square root of 16 times square root of 2. Can't forget the plus or minus when I'm square rooting an equation. So this will be plus or minus 4 radical 2. So just to answer our real life problem, these are the times, whatever time 4 radical 2 is and 5, that our inflation is at a rate of 0. So if you are doing the CP non-honors version of this course, then we're going to do one more example on these solving by factoring type of equations. If you're doing the honors version, you can skip this problem and move on to the next one. So we want to solve this equation, and as the title here suggests, we have something in quadratic form. First exponent is it's twice the second exponent, and then we have a constant. So with that in mind, and knowing what you know about these types of factoring situations, pause the video and see if you can solve this one. Alright, so I'm going to treat this like a quadratic, only I'm going to use x squared instead of x when I break this thing up. So let me just use some regular factoring reasoning. What are two numbers that multiply to negative 80 and add up to negative 16? Well, let me think. 1 and 80 doesn't work. 2 and 40 is no good. 4 and 20. If I have positive 4 and negative 20, that'll get me negative 16 by adding. So I can split this up into x squared minus 20 and x squared plus 4. And it doesn't really matter what order we write those in. Now, just like before, I can zero out each of these since they're down to a quadratic. So I've got x squared minus 20 equals 0, so x squared equals 20. And while I'm at it, I'll come back to solving this one. I've also got x squared plus 4 equaling 0. I'll solve this one as well in just a moment. So now x squared minus 20 equals 0. Add 20 to the other side for sure, and then square root both sides. This is kind of like the square root of 32 situation on our last example. We need to split this up into a perfect square times something. So 4 and 5 will do it for 20. So we've got plus or minus the square root of 4 times the square root of 5, which gives us plus or minus 2 radical 5. So just like the last equation, this one we couldn't get by factoring. We had to use square rooting to get these answers. Now this next one is even more interesting. If I subtract 4 from both sides and square root, 4 is a perfect square. However, this is negative 4. That means I'm going to have to take an I out when I square root this thing. So this is going to end up being plus or minus 2i. So two of the answers for this one weren't even real. So if you are doing the CP version of this course, you can stop here for now. This is the end of part 1. Pause the video, do some solving by factoring sort of homework examples, and then come back to do a little bit of graphing with us. If you're doing the honors, again, move on to the next one. We've got some more to do here. So welcome back. If you're doing the CP version of the course, this is your part 2 beginning here. Thanks for staying with us. If you were doing the honors version, let's talk about multiplicity and root behavior. We're going to be doing some graphing of polynomials that are starting in standard form. And one thing we're going to need to know is when we break these things up into intercept form, how is the polynomial interacting with the x-axis? And to understand that, we need to talk about something called multiplicity. So multiplicity is just a fancy way of saying the number of times a root appears for a polynomial. So for example, let's say you have x minus 3 quantity squared, and you're setting that equal to 0 and solving it. So obviously 3 is your answer, but it's actually 3 and 3. There's actually 2 answers. They just both happen to be the same number. So another way of saying that is we would have a root of 3 with a multiplicity of 2. This is a way of talking about duplicate solutions. So one question we might ask is, does the number of times a root appears for a polynomial affect how that polynomial behaves when it hits the x-axis? Certainly we're going to touch the x-axis at x equals 3 for this one, but are we going to go through or bounce or do something else weird? So to explore this, I'd like you to pause the video, go to Desmos, and graph out f of x equals x minus 3 to, we're going to call it p. You can plug in any number you want or make a Google or a Desmos slider for that, however you want to handle it. But plug in the numbers 1 through 8. See how that graph interacts with the x-axis, and then maybe see if you can draw some conclusions about the type of number this is and how things are behaving. So I'm going to show you Desmos on my end of it as well, just so we can compare notes here. So we've got f of x equals, and then I said x minus 3 to the, we'll start with the first power. And I mean, we have a line going through x equals 3. That's cool. If it's second power, now we have a parabola bouncing off of that spot. Third power, now we have, we're crossing through, but we're kind of flattening as we do it. Fourth power, kind of back to a parabola. Fifth power, still doing that flattening but crossing sort of thing. Sixth power, parabola. Seventh power, we're back to that. Eighth power, we're back to a bounce. So we keep going back and forth, and in fact, if you made like a slider P and just started like changing this up, you're going to notice that we are just going back and forth between bouncing and crossing through at a flattening sort of angle. So conclusions we can draw, the big takeaway from this is that if we have an odd multiplicity like 1, 3, 5, 7, whatever, the graph is going to cross the x-axis. And we could go a little bit further and say that for first power it just crosses straight through with no fanfare. For third power and higher it's kind of flattening, but it's still crossing through. And then for even multiplicities, our graph is going to bounce off the x-axis. So knowing this little distinction is going to come in handy when we actually graph these things out fully. So at this point, we are going to do a little bit of graphing of polynomials in standard form. Now, when we graph polynomials, at this point in the game, there's a few things that we want represented in our graph. We want a few places to anchor our graph. So we want x-intercepts, and if we can find them, we'd also like a y-intercept. Both types of intercepts would be groovy. We also want to know what the end behavior is as I go to the far left and the far right. What's my graph doing? And we also want to kind of know what's happening in between. Specifically, when I do hit the x-axis, am I crossing or bouncing off the x-axis? So if we know those four things, that'll help us to graph out something approaching a nice sketch of this. So first step is we would like this to be in intercept form because that's the only way we're going to be able to find the x-intercepts and also that kind of root behavior that we were talking about. So we're going to factor to find the roots on this one. Pause the video and see if you can figure out the x-intercepts for this. All right, so going through kind of our factoring techniques, we see that all of these terms have an x to the third power at least. So taking out a common factor of x cubed seems like a good move. And let's make it a negative x cubed so we can make this first term positive here. So if I take a negative x cubed out of everything, that'll give me a positive x squared minus 7x plus 10. And it looks like I can factor the insides here a little bit more. Numbers that multiply to 10 and add up to negative 7. That would be negative 2 and negative 5. So we have negative x cubed, x minus 2, and x minus 5. That gives us the x-intercepts of 0, 2, and 5. Those are our three roots. This 0 is coming from the negative x cubed. Negative 0 to the third is 0. So let's put those on our graph. So we've got 0. And I don't have any grid lines here. We're just going to sketch things and make sure things are in the right direction. So 2 should go somewhere over here, and 5 should go somewhere to the right of 2. Not needing to be too detailed here. It's just a sketch. They literally said sketch. Okay, now how about y-intercept? Let's talk a little bit about the y-intercept. So the y-intercept is the place where x equals 0. It's the place where your x value is 0, so that tells you where you are on the y-axis. So you could plug in 0 for x. If something's in standard form, though, every time you plug in 0 for x, you're going to zero out everything except a constant that's at the end here, if there is anything. So if we are in standard form, your y-intercept is just going to be the constant. In this case, that's an invisible plus 0. Now, in this case, 0 y-intercept doesn't give us any new information. So although the y-intercept is y equals 0, we've already got a dot on the y-axis there, so we can move on to the next step. But on other problems, we'll see this gives us a nice point here that's not on the x-axis, which is always good to have. The next question we're going to address is the end behavior. What is this thing doing as I go to the far left and the far right? We did a little bit on end behavior a few lessons back. Pause the video and see if you can figure out the end behavior for this polynomial. So remember, with end behavior, we're looking at the lead term, the exponent and the sign of the lead term, at least when this thing's in standard form. If it's in intercept form, you would have to multiply all the x's together to figure out what that lead term would be. But here it's already kind of spelled out. We have a negative x to an odd power. Negative x to an odd power means we've got a down line sort of situation going on. And just to review, if this were positive, we'd be going down to up sort of thing. And if this was an even exponent, it would either be an up parabola or a down parabola end behavior based on the sign. So we're going to be starting above our last point and ending below it is what this end behavior is telling us. Now the last piece of this is the root behavior, and for that we're going to use the multiplicity of our factors that are in factored form. So based on our discussion of multiplicity on the last slide, pause the video and see if you can figure out for 0, 2, and 5 whether we should be crossing or bouncing at each of those spots. All right, do you think you have it? Well, since these all come from odd factors, we have third power, this is an invisible first power, another first power. Since these are all odd factors, that means that we are going to be crossing for all of these. And specifically, if we want to be super detailed, we're going to be crossing and flattening at 0 because of this cube, although it's not a huge deal if you just kind of go straight through without that elegant flattening sort of look. So putting it all together, we are starting above, we are flattening through 0, coming down a little bit, crossing through 2, going up and crossing through 5, and we're ending below just like we said we would. Now, if you start in the correct place and make all the right decisions at each x-intercept, you should end in the right place as well, but it's always good to double check that. So we're going to move on to a few more graphing examples. Before we do those, some of you might be wondering, I get asked every year, how do you know where to turn around? Like this spot right here, why not, somewhere lower or higher up? The short answer is we don't really know where to turn around unless we plug in some more x values and get some more specific points. We're just sketching though, so you knew you needed to turn around at some point to go back through this x-intercept, so just pick a spot and go with it. So for this next example, this is an additional graphing example. If you're taking the CP version of this course, please do this one with me. If you're doing the honors version, you can skip on to the next graphing example. So with that said, if you're doing the non-honors, pause the video and see if you can graph this thing out. All right, so first step to do this, we want to put this in intercept form by factoring it and then getting the x-intercepts. Since I've got 4 terms, this would be a good factoring by grouping candidate. For the first 2 terms, I can take an x squared out of those, and that'll leave me with a 5x minus 2. For the next 2 terms, I really can't take out a whole lot other than maybe a negative 1, but that also leaves me with 5x minus 2, so that works out. 5x minus 2 is coming out of everything, and that leaves x squared minus 1 as my other factor. So at this point, if you remember kind of our discussion of solving polynomials, it is tempting just to solve this x squared minus 1 by directly setting it equal to 0 and using square rooting. I'm going to caution against that though, because later on when we talk about root behavior, we're going to want to know what this thing factors into. So I'm going to say lean on the side of factoring as much as possible when you're doing all of this solving in order to graph a polynomial. So we're going to still have the 5x minus 2, we'll bring that down, and x squared minus 1, we know that we can split that up into x plus 1 and x minus 1. So fully factored. This gives us zeros, roots of, let me think here, if I add 2 and divide by 5, that's 2/5, that's kind of a weird one. Next we have a negative 1 plus 1 would give us 0, and then 1 minus 1 would zero out this last one. So just going from left to right and putting these on our graph, -1 needs to be somewhere on the left of the y-axis. Again, it's just a sketch, so just eyeball it. Next, on the right side, 2/5 is less than 1, so we have 2/5, and then somewhere to the right of that we have 1. Now we can also get the y-intercept out of this thing. You might have noticed we have a constant of 2 up here. That's all that will be left if I zero everything else out by plugging in 0 for x. So 2 is going to be my y-intercept. And that's going to be somewhere up here above the x-axis. Again, don't think too hard about exactly where to put it, just right general location. Let's talk about end behavior now. Our lead term is 5x cubed. That is a positive x to an odd power. That means we're going to have an upline sort of end behavior going on, starting low, ending high. And then finally, for the root behavior, all of these factors are first power. They're all odd. So that means we're going to be crossing through every single one of these roots. So starting low, going through -1, going through our y-intercept, coming back down to go through 2/5, turning around somewhere, going back through 1, and we end up just like we expected we would. We're going to do one more graphing term here, even more graphing. Get it? Because we've got even exponents. So pause the video and see what you can make of this even polynomial on the graph. All right, so let's factor and solve this thing first. This one is a 4th power, 2nd power constant pattern. That's quadratic form. So let me treat this like a quadratic and use x squared instead of x for my initial pass at this. So let me think here. I'm looking for things that multiply to 16 and add up to -8. Well, -4 and -4 would do the job there. So I can break this up into x squared minus 4 and x squared minus 4. Now each of these can be split up a little further. We still have a difference of squares here. So this is going to be x plus 2, x minus 2, and then we have another x plus 2, x minus 2. Now I'm going to condense this a little bit. Since I have 2 of these x plus 2's, I can make that x plus 2 quantity squared, and I can do the same thing with the x minus 2's. So this gives me 2 roots. If I set these equal to 0 and solve, I've got roots of -2 and +2. Putting those on my graph, -2 is somewhere over here, and +2 somewhere over here on the right side of the y-axis. For the y-intercept, we've got the constant 16 we can pick out there. That'll go somewhere above the x-axis. For the end behavior, this is a lead term of x to the 4th, so that's a positive x to an even power. That means we're going to have an up parabola sort of shape to this thing if we zoom out far enough. So we're ending and beginning above the x-axis. And now for the root behavior, both of these roots came from even-powered factors. Since that's an even multiplicity, we're going to bounce on both of those roots. So starting above, we're going to come down and bounce off of -2. We're going through our y-intercept of 16, coming back down and bouncing off of 2, and ending above the x-axis as we said we should. So this is the end of the part 2 for the CP non-honors version of the course and part 1 for the honors version of this. Pause the video, do some practice problems, and then join us next time where we will talk about the rational roots theorem, which is what we're going to use when these traditional factoring techniques are of no avail. Welcome back. You're rejoining us for the next part of this lesson on solving polynomial equations. In this one, we're taking a look at the rational roots theorem. So here's where this is all kind of coming from. So we already know that if we know one root of a polynomial, which we'll call p of x, then we can use it with synthetic division to factor that polynomial down. And this is great as far as it goes. But what if they don't give us one of the roots or one of the factors? Then it's not very helpful. Now we could, if we wanted to, test numbers to see if they are roots, but which numbers are we to try? There's a whole lot of numbers out there, like an infinite number of them. So do we just randomly test numbers and hope something works? Well, it turns out there's a more systematic way to do this. To see where this way is coming from, observe the polynomial p of x and its factorization down below. So we've got 9x cubed plus 15x squared minus 8x minus 4 equals 0. And let's say that we actually were able to factor this thing and that we get the following. So 1x plus 2, 3x minus 2, 3x plus 1. Where is this factorization coming from? Who knows, but it is the true factorization. Feel free to multiply it out if you don't believe me. So if we were to solve this for the three roots, we would be zeroing out each of these parentheses. So this first parentheses, we would subtract 2, divide by 1, so that would be negative 2 over 1. For the next one, we would add 2 and divide by 3, so positive 2/3. And then for the last one, we would subtract 1 and divide by 3, so negative 1/3. So these are our roots. Now the million-dollar question is, can I look at my starting equation here and figure out what the roots should be? Kind of, sort of. So let's take a look first at the numerators of all these roots. And you'll notice I kind of color-coded things here in red and blue. And there's a reason behind that. So these numerators, they all came from these constants in this factorization. And these constants were all factors of this negative 4. That's where they came from. If you multiply all of these together, 2 times negative 2 times 1, that's where this negative 4 is actually coming from. So we see here that all of the numerators are factors of the constant right here, which is good information. So if I saw a numerator that was not a factor of this constant, then I would know that whatever root I was seeing was not actually a possible root of this thing. Now let's look at our denominators, because we can go a little further. All these denominators came when we divided by these blue coefficients here, 1, 3, and 3. And all those coefficients, if you multiply them together, would have given you this 9x cubed here. So that's telling us that all of these denominators from these coefficients, they are all factors of the lead coefficient in the original. So if I saw, for example, a 5 down here, 5's not a factor of 9, so I would know that that couldn't be a real root. So this leads us to something called the rational roots theorem. Here is the rational roots theorem. It says if a polynomial has rational roots, and that's a big if, they don't all, but if they do, they will be positive and negative, plus or minus factors of its constant, like this 4, divided by factors of its lead coefficient, like this 9 here. For example, the possible rational roots list, and we can generate a list for any polynomial, but for the one that we looked at up here, would be as follows. You would have factors of 4, plus or minus factors of 4, over factors of 9. And we're going to set up several of these PRR lists in the problems to come, but this is just kind of an introduction. So what are the factors of 4? Well, we've got 1 and 4 and also 2, 2 times 2. So 1, 2, and 4. How about the factors of 9? We've got 1, 3, and 9. So not a whole lot of factors individually. Now we're actually, to generate the list, we have to combine all these together. So we have 1, 2, and 4, all of them divided by 1. So that would just be 1, 2, and 4 if we reduce it. We also have 1, 2, and 4, all of them divided by 3. So 1/3, 2/3, 4/3. And then finally, we have 1, 2, and 4 divided by 9. So 1/9, 2/9, and 4/9. And sometimes you have to double check because every now and then you can reduce something in your list to a number that was already in your list. In any case, this is the list of all the possible rational roots. So if I were going to try to start plugging numbers in to figure out one of the roots of this polynomial, I would limit myself to this list. And if I didn't get anything on this list to work, then I would assume that there was no rational roots. So this is kind of handy. There is one little catch though. This reasoning only works for rational roots. It's not going to catch irrational or imaginary roots, which you may very well have. Now that we've had that little introduction to the rational roots theorem, let's see if we can put that into action. So we've got this polynomial here that we're trying to find the solutions for. And just taking a look at kind of our list of factoring techniques. So there's no common factors I can take out of all of these. There are 4 terms, but if you try grouping on this, I mean, you can take out an x squared here and get x minus 8. You can take a 1 out here and get 11x plus 20, but that's not going to really let you go any further with grouping. It's not in quadratic form. It's not even like some weird cubic shortcut or anything like that. So in this case, if no other factoring techniques work, that is when we turn to the rational roots theorem and start generating our list to basically guess and check. So first thing we'll do is actually write that PRR list, possible rational roots. So pause the video real quick and see if you can come up with the list based off of this one. All right, so remember we have factors of the constant, which is 20, over factors of the lead coefficient, which is just 1. So that's kind of nice. Factors of 20, we're going to have 1, 2, 4, 5, 10, and 20. There they all are. And it's good to kind of generate these in pairs. So 1 times 20, 2 times 10, 4 times 5. Less chance of missing something if you do it that way. All right, so what do we do with this list? So we are going to plug our list numbers into the function, which is the polynomial here, until we find a root. And we'll know we found a root if we plug one of these in and we get a result of 0. So let's go to Desmos and do that. So here I am on Desmos. I am going to just create a function for my polynomial. So f of x equals x cubed minus 8x squared plus 11x, and then we have a plus 20 going on as well. And then I'm just going to start plugging in numbers using my f parentheses notation here that are on this list. And if I get through all these numbers and none of them works, then that means there are no rational roots, and I'll have to maybe come up with something else. But let me start with my numbers. I always start with the 1 and the -1, and I just go from there. The reason I do that, I mean, you could plug these in any order you wanted, really. But first off, it's kind of systematic if you go from left to right, so you're less likely to miss one. Also, eventually you are going to be, if you do get one that works, you're going to be using synthetic division with it. So if I can get a smaller number that works with synthetic division, that's going to be a lot easier than, say, if -20 is what I have to use. So let me start with 1, and that gives me 24. So that's not what I need. Let me try -1 now, and that does give me 0. Awesome. So I'm going to write down, calculator says f of -1 equals 0. That's my way of showing people where my brain is at. And then once we have that number, we are going to use this root we just found, -1, to factor this polynomial with synthetic division, as we did in an earlier section. And then once we factor that down with synthetic division, you're going to solve your quotient for the remaining roots. So pause the video, see if you can execute that, and let's bring it back together and figure it out. All right, so if I'm going to do synthetic division, I need to write my coefficients. So we have a 1 for the x cubed, -8 for the -8x squared, we have an 11 and a 20. And my k value, my box number here, is going to be this -1 that I just found, because I know that should give me a remainder of 0. So let me do my line and bring down my first coefficient. -1 times 1 is -1, plus -8 is -9, times -1 is 9, plus 11 is 20, times -1 is -20, plus 20 is 0. So this is a surprise to nobody because, again, if you plugged the number in and you got 0, that means your remainder also should be 0 by the remainder theorem. But now let's see what this gets us. This means that x minus -1 or x plus 1 is one of the factors for this thing, and the other factor is this quotient. So this 1 represents a 1x squared because we're one exponent lower than we started with. Then we have -9x and plus 20. And let's just keep going. This looks pretty factorable. So I have the x plus 1, and now I need two numbers that multiply to 20 and add up to -9. So that should be, let's see, 1 and 20 doesn't work, 2 and 10 doesn't work. 4 and 5, if they're both negative, would give me -9. So we have x minus 4 and x minus 5. And then zeroing each of these out, we have x equaling -1, +4, and +5. Now, if you were using Desmos and you plugged in 4 and 5 to this function, you should also get a 0. Let me just show you that. So f of 4 was 0, f of 5 also 0, and just as a further sanity check, 4 and 5 are on your possible rational roots list. If you got a rational number down here that was not on your list, that would be another indication you need to go back and fix something. Now, since I just showed you plugging 4 and 5 into Desmos, you might be thinking, well, why didn't I just do that in the beginning? I mean, they're on my rational roots possible answers list, right? Why not just plug all these answers in and then just write down whatever ones end up working? Well, the trouble with that is that we're not guaranteed that all of our answers are rational roots, like 4 and 5. We might have irrational or imaginary answers, and this won't get them. So really the most tried and true technique is to go to synthetic division as soon as you can and get down to a quadratic as soon as you can, and then solve it using all of our quadratic methods. If factoring works, great, but you might need to use square rooting or quadratic formula as well. All right, we've got ourselves another example here. Pause the video and see what you can do with this one, finding zeros for f of x. All right, so for this one, again, going through our list of factoring techniques, grouping won't work if you try it out. Neither will common factors or anything else. So we generate our PRR list. So we are going to have plus or minus factors of 50 over factors of 1. So factors of 50, we've got 1. We've got 2 goes into 50. 3 doesn't work. 4 doesn't work. 5 works. 5 times 10. And then we had 2 times 25 and 1 times 50. And all of that is going to be over factors of 1. So if you're thinking, well, this is kind of boring if it's just everything divided by 1, well, count your blessings. Sometimes excitement is not what we need when we're doing these problems. But anyway, this is all just these numbers without the 1 underneath. Or the 1's invisible, we don't really need it there. So now we go to Desmos and try out however many of these we need to. So we've got f of x, and that's actually their name for the function this time. We didn't just make it up. That's going to equal x cubed minus 6x squared plus 9x plus 50. All right, let's plug in some numbers. So we try 1. 54, that's not what we need. We try negative 1, that's 34. Nope. How about 2? It's next number on the list, 52. How about negative 2? Can I get a negative 2? Ah, that works. Okay. So f of negative 2 was 0, so we're going to try negative 2 out with synthetic division now that we've established it'll give us something good. And if you didn't have a calculator available to try all these out, you could try every last one of these out using synthetic division. This is just a little bit faster with the calculator if it's available. So we've got our coefficient of 1, negative 6, 9, and 50. And negative 2 now is our k-value up here. Let's do our line and bring down our first coefficient. Negative 2 times 1 is negative 2, plus negative 6 is negative 8, times negative 2 is 16, plus 9 is 25, times negative 2 is negative 50. This is a good sign. This is adding up to 0 for our remainder. So we've confirmed that this is one of the roots. We have x plus 2 as a factor. And then 1x squared, just like on the last example, minus 8x plus 25, all of that equaling 0 now. So if we try to factor this down, and it looks like we should at least try, we're looking for numbers that multiply to 25 and add up to negative 8. Well, 1 and 25 doesn't work. The only other option is 5 and 5, and that also does not work. Since that doesn't work, we're going to use the quadratic formula on this one, or you could use completing the square, same idea. So we're going to have negative b plus or minus square root of b squared minus 4ac all over 2a. Little review from our quadratic days. This is going to be negative 8, that's our b value, plus or minus square root of negative 8 squared minus 4 times the a value 1, invisible 1 here, times a c value of 25. All over 2 times the a value 1. Simplifying a little bit, we've got positive 8 out here, plus or minus square root of, this is 64 minus 100, so that's negative 36, and that's all over 2. Square root of 36 would be 6. Since there's a negative, we have an I that's coming out, so this is 8 plus or minus 6i. And we'll simplify this a little bit more in a minute. So just writing our answers out now, we have x equals negative 2, which we found before, and then this is going to be 4 plus or minus 3i. And this goes back to that question some of you had from that last example of why not just plug in all the rational possibilities? Well, because here we see one that was not rational or even real. So again, this is why it's good to get it down to a quadratic and then do something else. So for those of you taking the CP non-honors version of this lesson, this is actually the end of the lesson. Congratulations. You can stop now and try out a homework. For those of you taking the honors version, we've got one more final boss battle, so stay tuned for that. So here we go, Algebra 2 Honors Final Boss. This one is a lot, so take a moment and just satisfy yourself that there is no way other than rational roots to approach this thing. We can't take out any common factors. There's no grouping or anything that would work on this, so rational roots it is. Let's come up with our PRR list, and we'll do a lot of this together, and then I'll have you try the rest of it on your own. So we have plus or minus factors of 9 divided by plus or minus factors of 2. Well, 9 is pretty straightforward. That's just going to be 1, 3, and 9. 2 is even more straightforward. That's just 1 and 2. So this starts innocently enough. So we have 1, 3, and 9 over 1. That's just 1, 3, and 9. We have 1, 3, and 9 over 2. That's 1 half, 3 halves, 9 halves. So no big deal there. Hoping we don't need to use those fractions in synthetic division, but we'll do what we need to do. So let's start plugging these into our function here. And this is where the calculator is super nice. So we've got f of x equals, this time around, 2x to the 4th minus 7x cubed plus 9x squared minus 21x plus 9. And let's plug in 1 to start with. Gives us negative 8. Let's plug in negative 1. 48. How about 3? 0. All right. So we got our 0. F of 3 is 0. So let's use synthetic division on that. Coefficients, we've got 2, negative 7, 9, negative 21, and 9. Plugging in 3. Bring down our first coefficient. We've got a 2. 3 times 2 is 6, plus negative 7 is negative 1, times 3 is negative 3, plus 9 is 6, times 3 is 18, plus negative 21 is negative 3, times 3 is negative 9. Adds up to 0. Awesome. So we've got x minus 3 as a factor, and this is going to be 2x to the 3rd, 1 less than x to the 4th, minus 1x squared, plus 6x minus 3. All of that equaling 0. So we've got it broken down to a cubic here, and you might be wondering, okay, what do we do at this point? We don't have a ton of methods for cubics. So if there is an easy shortcut you see here, you could take it, or you can do rational roots theorem again and hope that something will work. So what I'm going to do, if I'm going rational roots again, I'm going to give this quotient a name. I'm going to call this g of x, just so I can quickly refer to it and talk about plugging things into it. And what I'm going to do at this point is just plug in more roots to this quotient and see if I can find another factor. Now, when you're doing this, you don't have to plug the entire list in again. You only need to try numbers that either worked the first time because they could work again, we could have a multiplicity that's more than 1, or numbers you haven't already tested. The good news is if you've tested something and it didn't work the first time around, it's not going to work for this smaller case either. So at this point, I'd like you to pause the video and try whatever numbers are left and go from there. See if you can solve this thing. Okay, now there is one other thing that might be worth mentioning, and it wouldn't have costed you a ton of time if you did it, but you don't necessarily need to try even the untested things on your PRR list if they would not be on an updated list. If you look at factors of 3 over factors of 2 on this smaller polynomial, well, 9, and by extension 9 halves, those aren't factors of 3. So you actually don't even need to try the 9 and the 9 halves ever, once you've got it broken down to this smaller thing. But let's try some of the other things. So let's go to Desmos. Here's the f function that I had before. I'm going to clear all of that out. I do not want to try things again in that function. I want to try things in the g function now. And the reason I'm being really precise about this and not just being lazy and reusing the f function is if I try a duplicate root, I'm not going to see whether it still works in the quotient if I just plug it into the original function. So we've got 2x cubed minus x squared plus 6x minus 3. And let's plug in, let's see, the last thing we plugged in was 3. That worked the first time. It is not working this time around. It gives us 60. So let's try negative 3. Doesn't work. We said that we don't actually have to plug in 9, so let's go straight to 1/2. And that gives us a 0. Okay. So g of 1/2 is 0, so that's what we're going to use in synthetic division. So we've got our coefficients of the quotient now, 2, -1, 6, and -3, and we're using 1/2 as our k value. So there's our line. Bring down the 2. 1/2 times 2 is 1, plus -1 is 0, times 1/2 is still 0, plus 6 is 6, so far not too bad. Half of 6 is 3, plus -3 is 0. So we have the x minus 3 we originally got when we broke this down. We can write x minus 1/2 if we would like. And we've also got our quotient. This 2x is going to be actually 2x squared, one lower than the x cubed. This is a 0x we don't need to write. And we've got a plus 6. All right, so we can solve this thing now. We have x equals 3 from the x minus 3, 1/2 from our second parentheses, and I can write 2x squared equals -6. If I divide both sides by 3, I'm going to have x squared equals -3. And if I square root both sides of that, I'm going to get plus or minus I radical 3. And that is all of our roots. So we're just about done, but before I end this thing, one thing worth noting, just kind of rewinding here, back here with the g function, if you actually tried grouping on this, it actually would have worked. So you could have used grouping. So it's always good to check that before you go another round of rational roots, or even one round of rational roots, unless they're telling you to use that method. But this still worked out for us. So until next time, now that we've gotten to the root of this one, until next time, Mr. Sutton signing off.